In example number 5, we have a car that is traveling down a steep hill of mass m. At the bottom of the hill, the speed is v, and the force exerted by the road on the car is F. The problem is asking for the radius of curvature of the dip in the road. So if we look at the situation, we have the car coming down and back up into here. If we look at the change in velocity, so final velocity minus your negative initial velocity, we have the acceleration pointing straight up towards the center of the curve. That would be our circular acceleration, our centripetal acceleration. So for the force diagram at the bottom, we'll have the force of the road on the car, which would be greater than the force of the earth. Okay, that force would be our normal force pointing up. We have this circular acceleration pointing up, and when applying Newton's second law, we have F minus mg is equal to mv squared over r, your centripetal acceleration. If they're asking to solve for the radius, okay, we rearrange the equation to be the radius is equal to mv squared over F minus mg. Now, these equations here will be relevant later on, so we're going to come back to them. Looking at part B, okay, they give you the data reading for the normal force in this case, or the scale, that the car is, for the scale reading measuring the force exerted up on the car. Now, one important thing here, when the speed is 0, we know that the scale reading is equal to 588. This is going to be important for a number of reasons, because when we look at that, we know that the force exerted up and the force of the earth are balanced. So F would equal mg, and we can actually determine the mass of the car, F divided by g, if we use 9.81. So we have 588 newtons divided by 9.81 newtons per kilogram. We're going to find out that the mass is approximately 60 kilograms. Now, in plotting the graph here, the reason you see the graph tightened up horizontally is because it shows the exponential nature a little bit better. Sometimes it's kind of difficult, but a dead giveaway here in case you can't tell from the graph if it's exponential or not. And I'm just going to throw in that 0 scale reading because it's going to be helpful. If you look at the difference between each scale reading, all right, at regular intervals, you're going to find that you can see it is progressively getting larger. All right, so this hints that it's not at a linear relationship, even though if the graph is spread out, it might look a little bit more linear. You can see that it is increasing exponentially. Now, the first thing we're going to test here is going to be, so if we look at this in terms of exponentials, the most basic we're going to look at is a squared relationship. So on the next page, we'll end up squaring the speed, right? And plotting the speed squared versus the scale reading on the next slide. From the prior page, we took that speed squared data and plotted it versus the scale reading. I also included on here 0 and 588 newtons and 0 meters per meter squared over second squared on the graph here. So when we plot that, we see that it is a straight line. So now we can write an equation for the slope of the line, and we can use that expression to help us determine the radius of curvature here. So the slope in this case is going to be 834 minus 599 newtons divided by 625 minus 25 meters per second squared, which would equal 0.39 newtons over 600, over meters per second squared. Now, if we simplify the units, we're going to get kilograms meters squared over seconds squared. I apologize, there's meters over seconds squared. And then on the bottom, it should be meters squared over seconds squared. So ultimately, this will be kilograms times meters would be our unit. So when we look at an equation for this, the slope of the line, y is the scale radian, so it's the force exerted. The slope is going to be 0.39 kilograms times meter. The speed is going to be v squared plus your y-intercept. Now, from the prior page, we found that when the speed is 0, the scale radian is 588, or mg, so we're just going to put plus 588, which would be the force exerted by the Earth, or the normal force when the speed is 0. So up here, I'll just put parentheses above it. In order to relate what we did in part A back to the slope equation, I'm just going to slide back for a moment. And we're going to take our expression here, Newton's second law, and we're going to relate it to the graph that we just manipulated. So looking at the graph we just manipulated, all right, we have y equals mx plus b. So I'm going to add mg to both sides here so that these two equations can look similar. So now we have the force is equal to mv squared divided by r plus mg. And we can see that the two are the same thing, except in this case, the 0.39 kilograms meters is your slope. So I'm going to take this expression, bring it over here, so it's a little bit easier to see. So we have force is equal to m over r, which is our slope, times v squared, which is our x value, plus mg. So we can see that Newton's second law relates directly to this graph the following way. All right, y is the scale reading, the slope is the quantity m, mass over the radius, x is your speed squared, and the y-intercept is mg. So in order to use the graph to determine the radius here, we know the slope from what we solved for is 0.39, which I'm just going to round here to 0.4 for calculation sake, kilograms times meter. That will equal the mass over the radius. Now, if the mass is 60 kilograms, and that information we got from the scale reading when the speed was 0 divided by the radius, we can solve for the radius to be 150 meters. This is a prime example of how you would use a manipulated graph and the slope of that to determine an unknown physical quantity. This type of problem you will see on an open-ended question on the AP Mechanics C test.